Okay, welcome to Robotics 1. In today's class, I'm going to look at an inverse kinematics problem that involves 6 degree of freedom robot. So first, we are going to look at inverse kinematics. For 6 DOF robot. And the idea here is, as we discussed in the last class, we are going to split the robot into a manipulator and a spherical wrist. So let me work out this problem from scratch. So first, let me draw the kinematic diagram for this robot. So in this kinematic diagram, I have the first prismatic joint, then I have a revolute joint, and then I have one more prismatic joint. So these are the first 3 joints. Now, afterwards, I have a spherical wrist. And I'm going to show you the spherical wrist. But I will draw this in a slightly disjointed fashion. So this is the spherical wrist. So the first joint of the spherical wrist, second joint of the spherical wrist, and then we are going to have the third joint of spherical wrist. So this would be my first prismatic joint, second revolute joint, third prismatic joint, and then I'm going to have the revolute joint, and revolute joint. So as you can see, this robot is fairly complicated. And the problem that we need to solve is we want to solve the inverse kinematics for this 6 degree of freedom robot. So what does that mean? That means the end effector position. So this is going to be the end effector. End effector position Px, Py, Pg, and maybe roll, pitch, and yaw values. So for an example, maybe you have roll, pitch, and yaw. These values are given. So end effector, yeah, that's correct. It's in the gimbal log, but let me set up the problem in just a minute. So that way the problem we can solve. Just wait a second. Let me set up the problem first. So in this particular problem, end effector position and end effector roll, pitch, and yaw is given to us. And we want to solve this problem. Now, here is the first most that we are going to split this robot into 2 parts. So the robot, the first 3 joints, they are called as the manipulator, and the last 3 joints, we are going to call them as the wrist. So this is the wrist. We are going to assume the manipulator is responsible for Px, Py, and Pz, and the wrist is responsible for roll, pitch, and yaw. So before we set up the problem, I want to tell you a couple of things. Whenever you have a complicated robot such as this, we always split the robot. So let me start with the first joint. So this is my first joint. So this is my inertial reference frame. And by now you are expert in drawing the coordinate frames. So I would just quickly go ahead and draw the coordinate frame, and you can check, and you are welcome to correct me if I'm wrong. You would clearly observe that all the four rules, they don't get satisfied at certain joint locations. So in that particular case, we have to translate the frames, and I will show you the translated frames, but I trust that you are able to translate the frame and perform the forward kinematics correctly. So this is the coordinate frame setup after all the translation of the frame is done. Now, one thing I want to show you here, and please understand, this is an important aspect, is right now we are looking at this robot that is split into manipulator and spherical wrist. So I have shown you the forward kinematic setup for the manipulator. And clearly, this, what you will do, step one, if you want to find out the inverse kinematics of 6 degree of freedom robot, step one is to solve forward kinematics for manipulator. Now, what does that mean? It means finding out 0h1, multiplying that by 1h2, multiplying that by 2h3, and following the convention and finding 0h3. Now, what I'm going to do is, rather than working out 0h1, 1h2, 2h3, I will go ahead and directly give you the value for 0h3. So 0h3 for this robot, 0h3 for this robot is going to look like minus sine theta 2, 0, cosine theta 2, cosine theta 2, 0, sine theta 2, 0, 1, 0, 0, 0, 0. I need to give you some dimensions here. So let me give you this dimension. We think, say, this is the fixed distance. This is going to be D1. This distance, I'm going to call as A3. This distance, I'm going to call, so D3, so I will call this D2. We'll call this D2. This distance, I'm going to call from here to here, I'm going to call D3. So this distance is D3. So I'm going to set up this problem with following px, py, pz's. It is going to be a3 plus d3 cosine theta 2, a3 plus d3 sine theta 2, then d1 plus, if you look at d2 plus c3, and this is going to be 1. So this part is the rotation matrix. So this part is 0, R3, and this is px, py, and pz. So what a z3 is the extension of the 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 last prismatic joint. So please remember, these are variables that change, or joint variables. Joint, I'm gonna call them prismatic. Joint prismatic variables, thetas, are joint revolute variables. And please note D3 is over here. So if there is no A2 in this setup, so D3 is over here. I mean, if you want me to change this A3 to A2, okay. So I would just change this to A2. But that is just the sign convention. Any other questions? Yeah, that will come later. So first, let me solve this problem on paper, and then we will look at how to solve this problem inside MATLAB. So step 1 is px, py, pz. So the idea is, first and foremost, let's write down, so how do we solve the inverse kinematics for the first manipulator? So as you know, px is given to us. So px is equal to a2 plus d3 cosine theta 2. Py is equal to a2 plus d3 sine theta 2, and pz is d1 plus, this is d3, this is d3, this is d3, and this is d1. Actually, yeah, I made a mistake. The d's are joint variables, so this has to be a2. So clearly this has to be a3. So I made a mistake here. Please make sure that you make this correction. So all a's are fixed. So please note, first is the prismatic joint. We would do the prismatic joint, and the extension of prismatic joint 1 is d1. If you look at the revolute joint, the revolute joint variable is theta 2. The distance from these 2 points, the points that I am highlighting here, So if you look at this point and this point, the distance does not change. That's why I'm treating that as A2. If you look at this joint from here to here, then the distance does not change. That's why I'm treating that distance as A3, which is fixed. But then you have a prismatic joint, and prismatic joint can extend, and that extension is D3. So please understand, this is the convention. And then now I think the problem setup should be correct. So this is, I was right, this is A3, this is A3, and then the last quantity here is gonna be D1 plus A2, D1 plus A2. So I want you to take a minute to look at this kinematic diagram. And since I have to go back and forth, take a moment to confirm that everyone understands the forward kinematics. D1 plus A2. D1 plus A2 is the vertical distance. I mean, this is the distance, D1 plus A2. So that is the Z distance from the base of the frame. And then you have the X distance and the Y distance. So these are given over here. So let me make this correction real quick. So this is A3 plus D3, A3 plus D3, and the last one is D1 plus A2. Yes, I would label the roll, pitch, and yaw in the kinematic diagram in just a second. So first, let me set up the problem in the position inverse kinematics. So let's identify what are knowns. So Px is given, Px is known, Py is known, Pz is known. So on the left hand side of the expression, Px, Py, and Pz are known. Now, as you know, A3 is a constant. So A3 and A2 is also a constant. So A3 is given to us. A2 is also given to us. So from this position analysis, I need to extract following joint variables. Joint variables are, I need to find out the value of D1, which is the extension of the first prismatic joint. This is the extension of first prismatic joint. Then theta 2, which is the orientation of second, that's a revolute joint. And then D3 is the extension of third prismatic joint. So these are the three variables I want to extract. And please understand, three equations, three unknowns. So this is my equation 1, this is my equation 2, and this is my equation 3. So finding out D1 is very simple. To find D1, D1 is equal to Pz minus A2. So my value of D1 is known. Second is I want to find out thetas. So what I'm going to do is I'm going to say Py divided by Px, Py divided by Px is going to be equation 2 divided by equation 1. So that gives me tan theta 2. So I can find out theta 2 as A tan 2 Py, comma Px. And that gives me the value of theta 2. Once I know the value of theta 2, I go to equation, say Px is equal to A3 plus D3. And note, theta 2 is known. So cosine theta 2 is now known. A3 is known. Px is known. The only unknown from here is D3. So to answer the question inside the MATLAB environment, and I would set it up. Once I solve this problem, I will go to MATLAB and I will show you how this problem can potentially be solved in MATLAB. But inside the MATLAB environment, I just have to code these three equations. And these equations are equation 4, equation 5, and equation 6. The next part is how do I solve the orientation problem? So before I go to orientation problem, did everyone understand? First, I need to find out the three joint variables, which is D1, theta 2, and D3. So everybody is comfortable in finding D1, theta 2, and D3. Any questions here? Theta 2 is from here. Yeah. A tan 2. Yeah, that's what I said. A tan 2, Py, Px. Okay. So, all right. Now, we'll talk about the linear algebra part a little bit later. But let me go to the next part. Now, here it comes the tricky part. So everyone pay attention. So what I'm going to do is I'm going to show the spherical wrist, and it was correctly pointed out that this spherical wrist is in the gimbal lock position. So I'm not going to solve this spherical wrist. I'm not going to solve this spherical wrist, but I will set up the forward kinematics equations in this configuration. Because if you recollect, this is the configuration that I used a few lessons ago to set up the forward kinematics of the spherical wrist. So what I'm going to do is I'm going to set up the coordinate system. This is my first revolute joint. This is my second revolute joint. This is my third revolute joint. Please note, the first revolute joint is perpendicular to second revolute joint, is perpendicular to third revolute joint. So let's set up the coordinate system. So I'm going to set up the coordinate system. And one important observation here, that the coordinate system 3 that was initially drawn at the end effector of the manipulator is now going to be at the joint. So it is extremely important to understand this is x3, this is y3, this is z3. So please note, the coordinate system which was here, the coordinate system which was at the end of the end effector of the manipulator is now at the joint. The second coordinate system, I'm gonna show you something like this. You can check if my coordinate system is incorrect, but this is the exact same problem that we solved. And you will notice that you will have to translate the frame to get to the correct configuration where all the 4 rules are satisfied. But nevertheless, you would get this answer, x5, z5, and y5. And then you have x6, z6, y6. So now here, the step is, second step, step 2, solve forward kinematics of spherical wrist. Now, the forward kinematics of the spherical wrist, so for that, what you need to do is you need to find out 3R, or say 3, let me show you, 3H6, which will be 3H4 multiplied by 4H5 multiplied by 5H6. But please observe, when you find out this big matrix, since it's a wrist, you are gonna get a matrix 3R6, and there will be 0, 0, 0. There will be 1 here, and there will be 0, 0, 0. So when you solve this 3H6, you are gonna get a rotation matrix, and then all the distances are going to be 0. Now, rather than calculating this 3R6 again, I would directly give you the value of 3R6. So 3R6 is going to be, you can verify this, and this is what we did. C6, this is cosine theta 4, cosine theta 5, cosine theta 6, minus sine theta 5, cosine theta 6. The second column looks like sine theta 4, cosine theta 5, sine theta 6, minus cosine theta 4, cosine theta 6, minus cosine theta 4, cosine theta 5, sine theta 6. And clearly, you don't have to remember this. You can use MATLAB, solve forward kinematics using MATLAB, and then you should be able to find out the answer. Plus cosine theta 5. Then you'll have sine theta 4, sine theta 5, cosine theta 4, sine theta 5, cosine theta 5. So this is the rotation matrix that you get over here after solving the forward kinematics. Now, next step, which is step 3, is set up inverse kinematics for orientation. Now, I want to be absolutely clear, and this would be a right time to discuss the coordinate system or rule pitch yaw type of argument for forward kinematics. So let me set up the problem. So the problem is given something like this, that your wrist orientation, clearly right now the wrist orientation is in the gimbal lock. So you will not get a meaningful solution. So say wrist orientation, it's something like this. So the wrist orientation is something like this. So this is the first revolute joint. This is the second revolute joint. This is the third revolute joint. And let me set up the coordinate frame. So this is Z6, X6, and you have Y6. So what happened that the wrist, which was initially here, and clearly this was a gimbal lock, that wrist got moved to perpendicular. So this is the final orientation, and this is the orientation that we have to solve. And let me extend this and connect it with the manipulator. So this is my manipulator. So this is the manipulator. And for manipulator, my inertial coordinate frame, please note, inertial coordinate frame does not move. C naught, X naught, and Y naught. So this is the fixed coordinate frame. Now, first and foremost, let me state the orientation of the end effector. So the orientation of the end effector is given in terms of maybe either a roll pitch yaw angle, or it is given in terms of maybe some sort of Cottonian, or maybe it is given in terms of some sort of action angle, or maybe rotation matrix. So the idea is, what we want to do is, let's find out the orientation in terms of the rotation matrices. So I'm gonna give you some, the orientation problem stated something like this, that I want the end effector to be oriented vertically. So the z-axis of the end Z6 should be aligned with Z0. So how would the rotation matrix would look like? The rotation matrix for this particular orientation is going to look like, and please note, sign convention is going to remain the same. X0, Y0, Z0, X6, Y6, Z6. So as you can see, X6 is in the negative X1 direction, in X0 direction. Y6 is in negative Y0 direction, and Z6 is in the same Z0 direction. So this is how the orientation matrix is given to us. So please understand, this guy is given. And this is the orientation of 0R6. So this orientation matrix is given to us. Now, how does that apply in terms of roll, pitch, and yaw? So if you think about it, roll orientation, and I'm gonna write this down over here. This orientation is roll. This orientation, actually I showed it in the opposite direction. This orientation is pitch. And this orientation is yaw. So if I were to give you in terms of roll, pitch, and yaw orientation, this problem would state something like this. End effector orientation is 90-degree roll. So -90-degree roll, then basically it will give you the pitch orientation of say minus um, so 90-degree. So just a second. I need to convert this direction cosine matrix into the appropriate roll, pitch, and yaw angles. So just give me a second. I'm gonna pulling my MATLAB, and then I will find out the appropriate roll, pitch, and yaw. So, but this is the direction cosine orientation. So this end orientation is given as in terms of this direction cosine matrix or the rotation matrix. So the idea is, for the time being, this is known. So this guy is known. Now, how should I, from this information, how should I find out values of theta 4, theta 5, and theta 6? So the question here is, given this end effector orientation, how do we find out theta 4, theta 5, and theta 6? Everyone understood this problem that I'm trying to solve? So a particular wrist orientation is given, and I need to solve the values. I need to find out values of theta 4, theta 5, and theta 6. So what I'm going to do is, next thing is, I will set up this problem something like this. Now this is an important step. Please note that this is 0R6, 0R6. This guy is -1, 0, 0, 0, -1, 0, 0, 0, 1. This is 0R6. This 0R6 can be written as 0R3 multiplied by 3R6. And I want you to understand 0R3 is known from step 2. Zero R3 is known from step 2. And here is 0R3. Can you see that this matrix, this 0R3 matrix, since we know the value of theta 2, this 0R3 is completely known. Any questions here? 0R3 is known. Are you with me so far? Since from step 2, we found out the value of theta 2. So I can plug in the value of theta 2 in 0R3, and my 0R3 will be completely known. 0R6 only have ones and zeros because that 0R6 frame is aligned with X0, Y0, and Z0. That is why it only has zeros and ones. Now, so this guy is known. This guy is known. So what I'm going to do in next step, which is step 4, I'm gonna write this equation 0R6 is equal to 0R3 multiplied by 3R6, and I'm going to invert or multiply left hand right hand side by the inverse of 0R3. So 0R3 inverse 0R3. So I get 3R6. Now please note, since it's an orthonormal matrix, the rotation matrix, that the inverse of the rotation matrix is nothing but the transpose of the rotation matrix. So you can actually do a transpose and that problem would still work. So this gives you 3R6. Now here is the thing. This guy is completely known because this guy comes from step 2. This guy is completely known. This is given to us. And this guy, we actually found out in the last step, which is 3R6. So 3R6, as you can see, this is a big expression. This is 3R6. This is the big expression that gives you the relationship because it's a unitary matrix. So it's an orthonormal matrix. That's why it's an A inverse. And this is the special case. That's why for the rotation matrices, the inverse is transpose because it's an orthonormal matrix. So I'll write down 0R3 inverse is equal to 0R3, and you are welcome to verify transpose as 0R3 is an orthonormal matrix. Okay, that being said, now let's look at the left hand side. The left hand side is gonna have some numbers. And to be honest with you, at this point, you would observe that this 3 by 3 matrix could be fully populated because even though 0R3 is a diagonal matrix, 0R, so 0R3, 0R6 is a diagonal matrix, 0R3 is a non-diagonal matrix. So at this point, you're gonna have this fully populated matrix. And this fully populated matrix needs to be compared with 3R6. Now let me pick up some key elements from 3R6. Especially, I want you to look at this cosine theta 5 term. So here, this is cosine theta 5. Then I want you to look at maybe this term, which is minus sine theta 5 minus sine theta 5 cosine theta 6. And then for a minute, I want you to look at this term, which is cosine theta 4 sine theta 5. And then still there are some terms here. And these guys are unknowns. These are unknowns. But these guys are knowns. So what I'm going to do is I'm going to compare term by term. So I'm going to pick up this number and I'm going to call this number C33. I'm going to equate C33 is equal to cosine theta 5. And from here, I can get the value of theta 5. Once I know the value of theta 5, what I can do is I can go to C23. C23 is equal to cosine theta 4 sine theta 5. Since theta phi is known, sine theta phi can be known, and cosine from cosine inverse, I can find out the value of theta 4. And last but not least, this is C third row first column, C31. C31 is equal to minus sine theta 5 cosine theta 6. But please note, theta 5 is known. So from here, I can find out the value of theta 6. So at this point, please note, all the joint variables are known. And those joint variables are D1, we found out. Then we found out theta 2. We found out D3. We got these from the position manipulator inverse kinematics. And then we found out theta 5, theta 4, theta 5, and theta 6 from the wrist inverse kinematics. Everyone understood this? Second row on this page, 0R3 inverse. Yeah, 0R3, 3R6. Yeah, that is correct. 0R3. Which question? I don't understand Kaji's question. You mean which part of the wrist is not correct? 0 C cosine theta 5. I'm trying to understand. So 3R6. Oh, yeah. I see. Yeah, this 3R6. Okay, 3R6. Yeah, you're right. 3R6. That why 3 gets cancelled. And yeah, so this guy is here. Okay. All right. So any questions on the forward and inverse kinematics here? So now the question is, how would we solve this problem using MATLAB? And if you understand the MATLAB equations solving process, let me share my screen, and then we will try to solve the inverse kinematics problem using MATLAB. So everyone understood the process. First, trying to solve the forward kinematics. Then second, we will find out the rotation matrix. Then we will solve for the wrist kinematics. And then later we will solve the inverse kinematics for the wrist. And then finally, we would do term by term comparison and then get the answer. So as my MATLAB is booting up, any questions? If you don't have questions, this would be a good time to start MATLAB. And I will try to set up the inverse kinematics problem for the rest. Yeah, slide 3. Any question? Okay, now I'm going to share my screen and I will share MATLAB. So for some reason, I don't see MATLAB. Okay. Okay. Can you see my MATLAB screen? Okay. So we are trying to solve the inverse kinematics problem. So first, let's code the equations, and the equations that need to be coded. So let me write down what is given. Px is given, say 0.1. So I would say given values. Given values. Px is given, Py is given, so 0.2. Pz is given, say 0.5. And we are going to solve Ik for manipulator. So the first equation that I'm going to solve is theta 2 is equal to A tan 2 Py comma Px. Py comma Px. Then d1 is equal to, then you have the robot parameters. So in the robot parameters, say A1 is, or A2 is given. A2, I'm gonna say 0.02. Then I'm gonna say E3 is equal to 0.02. So D1 is equal to Pz minus A2, and D3 is equal to Px minus, so no, Px minus A3 cosine theta 3 theta 2 divided by cosine of theta 3. Yeah, so this is from the inverse kinematics of the manipulator. So, and we can see if this works real quick. So theta, this would be theta 2. So I know the value of theta 2, I know the value of d1, I know the value of d3. Now next thing that is given, that the orientation of the wrist, orientation of the wrist, and orientation of the wrist is given in terms of the matrix, and I want you to go back and see this wrist orientation matrix, and I'm going to call this R06, which is given as -1 0 0 0 -1 0 0 0 1. So this is the orientation of the wrist. So IK for wrist, to find our IK for the wrist, the first thing is we need to find R03. R03 is given as minus sine theta 2 0 cosine theta 2 minus sine theta 2 0 cosine theta 2 cosine theta 2 0 sine theta 2, and last but not least 0 1 0. Everyone okay with this? So you would get 0 R3 theta 2, and yeah, you will have a multiple solution problem that we will solve in just a few minutes. Bear with me for a second. So everyone with me so far? 0 R3. So R36 is equal to R36 is equal to, and at this point I want you to try this. You can say inverse of R03 multiplied by inverse of R03 multiplied by you can say R06, and you can compare with this value, and I'm going to say 361 is equal to transpose R03 transpose multiplied by R06. And I want you to see that once you do all these, you get the same answers. So let's work out the problem this far. So let me say, okay, before I run the script, any questions here? So let's see what is happening with theta 2. Theta 2. So theta 2 gives me 1.17. Let's see what is the value of D1. D1 gives me 0.48. D3 gives me 2.36. Are these the values you got? Okay, now next part is, let me run R03. then I want to find out these two solutions, R36, and so when I evaluate, let me see, R06 I did not have in memory. So can you see that inverse and transpose, they give me the same answer. So finally, I have R36. At this point, I have R36. So what I'm going to do is to find out at this point, I'm going to say theta 5 is equal to R cosine of R36, third row, third column. So theta 5 is R cosine of R36, third row, third column. Then theta 4 is equal to, now theta 4 is, I need to first get to R06, second row, third column, R06, second row, third column, divide that by sine of theta 5, and then do arc cosine of the quantity. And please check. Okay, just a second. R36, correct, R36. Yes, I will post this code in Canvas. So R36, and to last but not least, to find theta 5. So theta 6 actually, theta 6. To find theta 6, I will have to do the same thing. R36 R36, but now what I need to do is third row, first column, third row, first column, divide that by, we know theta 5, so divide that by sine theta 5, and there is a negative sign, so minus, and then do a cosine of this quantity. So please check my equations just to make sure that my equations are correct. What I did, I just coded the equations that we obtained. And yes, I will actually save this code. So I will save this code. IK spherical wrist. And I will solve this problem. So once you solve, so let me see, I made a mistake somewhere, theta 4. Okay, yeah, so here is the mistake. This should be capital. This should be capital. And when you run, that should give you the solution. So now at this point, you have all these values. So you have theta, you have theta 2, D, so D1, theta 2, D3, theta 4, theta 5, and theta 6. Can you leave your MATLAB in file? I will upload the MATLAB file onto Canvas so that you'll have that for the reference. Any questions? Now, let me, at this point, if you don't have question, let me answer the question that I did not answer on the roll pitch yaw. So just say help. So as you can see, this is the command. So ROTM to EUL. So what I would do is, if you want to find out ROTM to EUL, and if you want to give your rotation matrix, so I would say R06. So this gives you the roll, pitch, and yaw for the rotation matrix. So as you can see, I gave the rotation matrix R06, and it gave me the rotation matrix. The default sequence is ZYX. So this value is the rotation about Z. This value is the rotation about Y. This value is the rotation about X. So please note, please observe this 3.14 in the radians is my yaw angle. 0 degree, which is the rotation about Y, is my pitch angle, and rotation about X, which is this guy, is my roll angle. So if you want to see, let me say that if I give you the problem something like this, position values are given to you as distances, but the orientation values are given to you as Euler angles. So let's look at this problem that given, say roll is equal to 0, pitch is equal to 0, and yaw is equal to 0. So at this point, there is an additional step that you want to do, is you want to say R06 is equal to EUL to ROTM, and now you want to specify, so help EUL to ROTM. In that case, you want to specify Z, which is yaw, ZY, which is pitch, and then roll. So this is about X, about Y, and about Z. So just to be consistent, I would just say 3.14. Yeah, now if you want to convert everything in degrees, so here is what you will do. So multiply thetas. You can actually, there is a command. So help a tan d. So basically, if you convert this to a cos d, a cos d, a cos d, now this will give you the values in degrees. So you can use the MATLAB command, a cos d, that will give you the values in degrees. So now you run. So invalid expression 11. So let me see R0. So you got these values. So you see this imaginary value, that is actually, that means it comes from the numerical integration or numerical solution, it will be 0. So these values are zeros. So, or what you can do is, as someone said, multiply this by 180 divided by pi, multiply this by 180 divided by pi, multiply this by 180 divided by pi. Line number 11, I did not close the parentheses. So now you should be getting the answer. So clear all, you'll see, and then you should be able to find out the inverse kinematics answers. So theta 5. Oh, so, and if you add these, I'll just leave it here for your reference. We want to convert that to degrees, or if you want them in radians, save. So let's find out R06. Okay, so yeah, from here. So as you can see, now here is a problem that I want you to understand, that because of we did not provide the absolute accurate value of pi, I got some spurious numbers, but those numbers, they are meaningless. That is because of the floating point arithmetic. So if you do it like this, and now if you run this code, you are gonna get correct answers. And I will upload this code into MATLAB. So I will upload this code. This is actually, for practical purposes, this is 0. This is coming because of so for assignment 2, if you have any questions, I have told Jesslyn to meet with each one of you, and each one of you, theta 4, yeah, theta 4 is 0. So each one of you and explain the problem. And if you have lost any points on the assignments, please work with Jesslyn, and she will explain what is missing, and then you can understand your grade. So please send her an email, set up a time. Jesslyn's email I will share in the chat window. Just a second. Jesslyn Samuel. This is her email. I'm going to stop recording, and I would be happy to answer any other questions that